This is the first lecture on 10-1, scatter plots and correlation. So we're going to start with the scatter plots, and we're going to take a look at something that is in your book. So if you have a bunch of points that look like they have a positive correlation, not a positive correlation, positive relationship. So it looks like if you were going to draw a line through those points, the line of best fit, and we'll want to do that in the next section, but I'm already starting with the lines. The line would have a positive slope. Hence, this scatter plot can be said to have positive linear relationship. If I have a collection of points that looks like this one is said to be negative linear relationship. Now let me give you two more examples. I could have something that looks like this. So it looks like it's going up and then down. So this is not a line. This is a parabola. The book calls it the curvilinear relationship. I'm going to say non-linear relationship. Because in our class, we're going to study linear and non. If anything, this is curvilinear. I can give you the one that is actually used a lot in the real world. It looks something like this. And it's an exponential. Relationship. Again, not something that we're going to study in this class. What we'll see in this class is one of the three. Positive linear relationship, negative linear relationship. So we'll draw a line like this. And something that might look like this. As in, it's a cloud. What we're going to say is no relationship. Your calculator and Excel will help you in graphing these out. The example in the book has a few data points with that you can use to construct a scatter plot. I am doing example 10-1. I have companies A, B, C, D, and F, D, E, and F, and I have the car rental companies in the United States for recent years, cars in 10,000s versus revenue. So the question is there a relationship between cars the rental company has and the revenue that it produces? You would think that there is a relationship. The more cars you have, the higher your revenue. So this is what we're trying to see. The data set is given as 63, 29, 20.8, 19.1, 13.4, and 8.5. This is going to be your cars. And as far as the revenue, each X has a corresponding Y. Generally speaking, the first column will be your X, the second column will be your Y, but it's up to the context of the problem to figure out which variable happens to be your independent one, which one you want to label as X, and which one is your dependent one, Y, meaning Y is expressed in terms of X. In this case, the way this book orients things, the thing that's written first, those are your X's, the thing that's written after it is your Y's. So what you can do is you can graph this by hand if you want to make sense of this, but really this is just a collection of points. So I'll label this as, let's say, 10, 20, 30, 40, a few more, 50, 60. And this one is 1, 2, 3, 4, 5, 6, and 7. And then I can see at 63 I'm up at the 7. That one's far. This is a sketch, if anything. 29 I'm almost at a 4. At 20.8 I'm about 2.1. At 19.1 I'm at 2.8, so there's that point. 13.4 is 1.4, and 8.5 is 1.5. So what I can see right here is there does seem to be a linear relationship. In fact, it feels like I should be able to draw a line right through those, right? So what this tells me, first of all, this is called a scatter plot. That's a vocabulary word. Second of all, it does look like I have a positive relationship. What I would want to do next is to actually be able to measure the positive relationship and give it a number. So that's called a correlation. And the correlation has a particularly ugly looking formula that is in your book on page 554. I'm not going to write it down. And the rest of the section actually explains how to, or 2 pages of the book explains how to use this formula algebraically. What I want to concentrate is what does it mean to be different kinds of correlation. And we'll start here. When r is equal to a 1, what it means is I have collinear points that have a positive slope. It doesn't have to be a slope of a 1, but it has to be positive and they have to be collinear. An r correlation coefficient of -1, it means that I have collinear points that happen to have a negative slope. A correlation of 0, it means that I have a cloud. This is correlation 0. A few other ones that are in between might look something like this. So something like this, where you could obviously see that it is that it does form a line, might have a correlation of 0.9, where a relationship that's a little bit more spread out but still has a positive trend might have a 0.7. So the closer you are to a 0, the more spread out, the more cloudy it looks. The closer you are to a 1, the more it looks like a perfectly collinear points, the perfectly good line. Your calculator will help you in figuring out the correlation coefficient, and we'll do that on the next video when I look at the calculator. But this particular example, notice that the points do line up pretty nicely, even according to my pretty bad sketch. The R does come out to be 0.982 according to the book. This might be a rounded a rounding, but it does look like it's pretty close to a 1, meaning it's a positive relationship. The more cars you have, the higher your revenue is. And because it is close to a 1, we would say that it does appear to be a strong positive correlation. Now, the significance of the correlation can actually be measured using a significance test, meaning in the book, it's under example 10-7. We can actually test the significance of the correlation of this example. So test the significance of R is equal to 0.982 in previous example. With a significance level of alpha of 0.05. The hypothesis for this is a row. I'm going to draw it like this. It's a funny looking P. And the alternative hypothesis, meaning, so the null hypothesis indicates that there is no relationship between the two variables. The alternative hypothesis says rho is not equal to a 0, meaning that there is a relationship. So this one says no linear relationship. This one says there is. The test statistic that is used in a regression analysis is actually a t-test statistic. So we take t to be r times test statistic, r times the square root of n minus 2 and 1 minus r squared. So this one is programmed under your linear regression test. With a degree of freedom of n minus 2. And it has to do with the fact that I'm talking about two variables, the x and the y. So you take one from the x, you take one from the y. So this is what made sense to me. It is always a two-tailed test. No, it doesn't have to be a two-tailed test. You can say that there is a positive relationship, so you'll say rho is greater than 0, or there's a negative relationship, meaning rho is less than 0. But all of the tests that are run in this book happen to be all two-tailed tests. So either there is a relationship or there is no relationship. Now, if I plug in all of the numbers into my calculator, into the formulas, the t-test statistic that comes out for this test does happen to be 10.398. And we'll take a look at the p-value once we run this test. But if you take a look at the critical value, you can either look it up under the inverse t under your calculator, or look back at the t-table if you'd like. I'm getting it from the book because I will do this example again on a calculator. The critical value does happen to be 2.776. So I'll do it using a p-value on the next video. And this 10 is really far away into the tail. So you do reject the null hypothesis, meaning there appears to be a strong linear relationship between the number of cars and the revenue. On the next video, I will actually go back to the same test and we'll go through all of the steps of 10.1, meaning draw out a scatter plot, find the correlation coefficient R, and run a hypothesis test of the significance of that correlation coefficient.